my YouTube viewers. It is Crystal. In this video, what we're going to be talking about is different sampling techniques that you can use for your statistical research activities. And these sampling techniques are going to be covered in the R programming language. And so the first sampling technique that we're going to cover is random sampling. So in random sampling, every member of the population has an equal chance of being selected. So we're going to go over a small program in R to talk about random sampling. So the first thing we need to do is we set the seed. So whenever you set the seed, that means that every time you run the program, it initializes to the same values. So set.seed brackets 1, 2, 3. And now we're going to set the population. So there's a difference between a population and a sample. So a population is every member, and then a sample is a sample of a population. So we're going to set the population as being 1 to 10. And then we're going to set that you've got two ways that you can set your sample. You can set your sample without replacement, and you can set your sample with replacement. So the first way that we're going to set the sample is without replacement. So we're going to sample 5 numbers without replacement. So sample no replace becomes sample brackets population, comma, size equals 5, comma, replace equals false. And then so when you print the results, when you print sample no replace, in this particular run of the program, it's going to be 3, 10, 2, 8, 6. And then now what you can do is you can set the sample with replacement. So your sample becomes sample brackets population comma size equals 5, replace equals 2. True. So basically what happens is every time you pull out a number, and then you replace that number with another number. So whenever you print this particular runoff, it's going to be 5, 4, 6, 9, 10. So, but we're going to try to run it again, see if we get a different samples. Because if you sample with replacement, in theory, you could have one number show up twice in the sample. So you've got 3, 10, 2, 8, 6 was the first one, and 5, 4, 6, 9, 10 as the second one. So what has happened is when it sets your seed, then it initializes the values to the same value. So we haven't got that. Let's just try 1 to 15. 1 to 15. Or let's just try 1 to 15. And sample size equals 10. Let's just try that. So for 1 to 15 without replacement, it's going to be 5, 3, 14, 10, 2, 6, 5, 4, 12, 7. So that's sample size with no replacement. But when you do it with sample size with replacement, you get 9, which appears 4 times, 10, 11, which appears 2 times, 5, 3, and 12. So that's what I wanted to show you, the difference between sample size without replacement and sample size with replacement. Because when you sample a number and you take the number out, then you put the number back in. That's with replacement. And so when you put the number back in, that means that that number can appear a second or third or even a fourth time, which is what we've demonstrated in this code. So here's a little program on sampling distribution so we can visualize it. So we set our seed as being set seed brackets 1, 2, 3. We have a population becomes 1 to 100. So we're going to take 1,000 samples of size 10 and compute their means. So sample means becomes replicate brackets 1,000 comma mean brackets sample brackets population comma 10 comma replace equals true. So again, this is you're sampling with replacement. And then what we're going to do, we're going to plot the distribution of the sample means, and we're going to do that on a histogram. So hist becomes sample means comma main equals sampling distribution of the mean comma x lab, that's your x label, equals sample mean, comma call, that's your color, equals sky blue, comma border equals white. And then so we print that off, we plot it, and then we plot it, we have a histogram. And so you can see that the histogram represents a normal distribution. And what this does is this demonstrates the central limit theorem. And so the central limit theorem is that when you take a distribution, and we can see when you take a distribution and you replicate and you sample it, the more times that you sample that distribution, then the distribution that's made resembles a normal distribution, which is what we've done because we sampled it 1,000 times. So we had a population of 1 to 100, and we sampled that 1,000 times with replacement. And so when we sample that 1,000 times with replacement, we get our histogram, which looks like a normal distribution. So this also, although it is randomly sampled, it also illustrates the central limit theorem. So now what we're going to talk about is we're going to talk about stratified sampling. In stratified sampling, population is divided into distinct subgroups or strata, and a random sample is taken from each stratum. So the first thing we want to do is we want to create a data set with a stratum variable. So df becomes data.frame brackets. IED equals 1 to 20, group equals rep, and rep means repeat, bracket C, and C means continuous or combine, brackets A comma B, brackets comma times equals C, brackets 12 comma 8, brackets comma, and you're going to have 12 in A and 8 in B. And then we're going to make a table of this data frame that we have created. So you can see that A you have 12 and B you have 8. So now we're going to have a small program with stratified sampling that is proportional. So the first thing you want to do is set your seed. So set.seed brackets 1, 2, 3. And again, that means that every time you run the program, it initializes to the same values in the elements. And then we're going to have the proportion to sample from each stratum. So prop becomes 0.25. So that means each stratum is going to be 25%. So we're going to sample with stratified sample. Strat sample becomes do.call brackets rbind. And then rbind means that you're going to combine the rows, comma L apply brackets split brackets df, comma df $ group brackets comma function. So we're going to make a function as well. Function brackets sub df brackets and curly brackets N becomes ceiling, brackets, in row, brackets, sub df, times probe, brackets, sub df, square brackets, sample, brackets, in row, brackets, sub df, brackets, comma, in, brackets, comma, square brackets, and then curly brackets and curly brackets. So this also is an example of using a function within sub df. Where is your sub df? I'm just looking for sub df because the function accepts sub df as input. That's what it does. And then so now we're going to run strat sample, and then which calls this function, and we're going to create a table of strat sample $group. But strat sample has a function in it, and this function accepts sub df as the input. And I don't really see a function sub df. Anyway, we'll just carry on with that. So with strat sample, you can see you've got your data frame, which is 5 rows by 3 columns. So it's going to be 3 columns are going to be integer, ID, a group, which is a character, and a value, which is a double, which is numeric. And so basically that's how you do proportional stratified sampling, and you can experiment with this if you like, because it's a little bit more complicated than the random sampling, definitely. And so now we have stratified sampling, which is fixed sample size per group. So set.seed, brackets 1, 2, 3. So what that does is every time you run the program, it will initialize to the same values, and fixed in becomes 3. So strat sample fixed becomes do.call, brackets, rbind, comma, lapply, brackets, split, brackets, df, comma, df $group, comma, function, brackets, sub df, curly brackets, sub df, brackets, sample, square bracket sample, brackets, in row, bracket, sub df, comma, fixed in, which is 3, comma, square brackets, curly brackets. So we say strat sample fixed. So what that we're doing now in this instance is that we're running the function. And then so we make a table of strat sample fixed and $group. So again, you have your you have so many rows. 1, 2, 3, 4, 5, 6. You have 6 rows and an ID column, which is an integer, a group column, which is a character, and a value column, which is a double. And then we find out that you have in A, you have 3 elements, and B, you have 3 elements as well. So you have a fixed sample size per group. The next type of sampling we're going to cover, and this is the third type of sampling, is systematic sampling, which is a random starting point is chosen and every K member of the population is selected. So the first thing you're going to do is you're going to set your seed, being set.seed brackets 1, 2, 3. And so that means that every time you run the program, it's going to initialize to the same values. So your population becomes data.frame, brackets, ID equals 1 to 30, comma, value equals rnorm, brackets, 30. So the value is you're going to have a normal distribution, random values in a normal distribution, and 30 random values. So you're going to have your systematic sample. And so, let's run this. So when your systematic sample becomes a function, data, comma, sample size. So your sample size is curly brackets, n becomes n row brackets data, k equals a floor brackets n oblique sample size brackets, that's your sampling interval, start becomes sample brackets 1 to k, comma, step 1, a random start between 1 and k. Indices becomes SEQ brackets start, comma, by k equals k, comma, length dot out equals sample size and data size indices. So we'll say we're going to say systematic sample. So we're going to say DF, population. And your sample size, we'll say it's going to be 3. So when we do it with the population as being your sample, that's your data, and the sample size being 3, you can say that the systematic sample brackets population, comma, 3. So you have a data frame of 3 rows by 2 columns of data. So your ID is integer of 5, 15, and 25, and the value is a double. But let's say if we make a sample size of 5. So when we make the sample size of 5, you've got 5 rows of data. So it starts, and you've got ID is your integer, and your value is a double. So the next thing we're going to do is we're going to set a sample size of set seed 1, 2, 3. Sample size becomes 6. And then we're going to say sys sample becomes systematic sample brackets population, comma, sample size, and that is its value of 6. And when it's a value of 6, you have 6 rows by 2 columns of data. And let's see what we've got here. And so that's just a little different way to do it, because in the first cell, in this systematic sampling, we said systematic sample population, comma, 5. And in the second cell, what we did was we said sys sample becomes systematic sample population, comma, sample size. And then we said the sample size was 6. So that's just a different way that you can write it. So if you want the sample, to actually be stored somewhere, then you're going to define the variable sys sample. And if you don't want it to be stored anywhere, then you don't have to define the variable. So that's just a different way that you can write it. So the next thing that we're going to have is cluster sampling, and this is the 4th type of sampling. So the population is divided into clusters, and a random sample of clusters is selected. So the first thing you were going to do is we're going to set our seed, and we set our seed so every time you start the program, run the cell, the variables are going to initialize to the same values. And then so we're going to create a population with 5 clusters. So population becomes data.frame, brackets, ID equals 1 to 30, comma, cluster equals rep, that means repeat, brackets 1 to 5, comma, each equals 6. That means you're going to have 6 clusters, and then comma, so it's going to be, 5 clusters, each with 6 people, so I got that wrong. And then value equals arc norm, brackets 30. So arc norm is a random selection of the normal distribution. So you're going to randomly sample a normal distribution 30 times. So we're going to make a table, and then when you make the table, population $cluster, it's going to be 1, 2, 3, 4, 5, and then it's going to be 6, 6, 6, 6, 6. So that's your table of your population and your cluster. So in order to demonstrate this, we're going to set the seed, brackets 1, 2, 3, the number of clusters to sample, cluster of sample becomes 2. So out of this population that has 5 clusters, each with 6 people, we're going to only sample 2 clusters. So we're going to randomly choose clusters. Selected clusters become sample, brackets, unique, brackets, population, $cluster, brackets, comma, clusters to sample, which is 2 brackets. And we're going to take all individuals from those clusters. So cluster sample becomes subset, brackets, population, comma, cluster, percentage, in percentage, selected clusters. So we're going to run the selected clusters, and we're going to run the cluster sample. So your selected clusters are going to be 3 and 2. And then your cluster sample is going to be a data frame with 12 rows by 3 columns. And because originally we had 5 clusters with 6 elements each in it, and so since we're going to be using 2 of those 5 clusters, so 2 times 6 is 12, so you're going to have 12 rows of data, and each of these rows of data is going to have an ID, which is an integer. It's going to have a cluster. It's going to tell you which cluster it's selected. So 6 of the rows are cluster 2, and 6 of the rows are cluster 3, and then it's going to tell you the values. And so the next time we're going to run it again. So set.seed is brackets 1, 2, 3, and cluster to sample becomes 2. Selected clusters becomes sample, brackets, unique, brackets, population, $cluster, comma, clusters to sample, which is 2 brackets. And sample 3 individuals from each selected cluster. So cluster sample partial becomes do.call, brackets, rbind, comma, lapply, brackets, split, brackets, population, comma, population, $cluster, brackets, square brackets, selected clusters, square brackets, comma, function, brackets, CL, brackets, curly brackets, CL, square bracket, sample, brackets, in row, bracket, CL. It's either a CL or a C1. No, it's a CL. Brackets, comma, 3 brackets, comma, square brackets, curly brackets. And then so we're going to say selected clusters and cluster sample partial. So your selected clusters, again, are going to be 3 and 2. And then, so we're going to sample 3 individuals from each selected cluster. So in this data frame, you're only going to have 6 rows of data And the reason for that is because it only selected 3 elements from the 2 clusters 2 and 3. So you've got your ID, which is an integer, you've got your cluster, which is an integer, and you've got your value. So your clusters are going to come from 3 and then 2. And then it also tells you, the row tells you which element of the cluster that you're actually selecting. And then so the last type of sampling we're going to talk about is convenience sampling. And in convenience sampling, the sample is selected based on ease of access and availability. So we're going to set our seed as set.seed brackets 1, 2, 3. So every time you run the cell, it's going to come up with, it's going to initialize the variables to the same value. And so population becomes data.frame brackets ID equals 1 to 30, comma, group equals rep, so that's repeat, bracket C equals combine, brackets A, comma, B, comma, C, brackets, comma, each equals 10. So that means you're going to have 30 rows of data, 10 rows are going to be A, 10 rows are going to be B, 10 rows are going to be C. And then your value is going to be R norm brackets 30. So basically what you're going to do is you're going to randomly select a normal distribution 30 times to give you 30 rows of data. So now what we're going to do is we're going to head brackets population. So head means it's going to select the first 6 rows of data, and the reason why is because you don't want to have 30 rows of data. So it's going to select the first 6 rows of data. And as you know, the difference between Python and R is Python, the first number is 0, and R is the first number is 1. So you've got your first 6 rows of data, you've got your ID, you've got your group, which is a character, and then you've got your value. But if you want to do this, so if you want to see the head and the tail, you can see the first 6 rows of data and the last 6 rows of data. So we're going to demonstrate the convenience sampling. We're going to take the first 8 rows. Convenience sample becomes population, square brackets 1 to 8, comma, square brackets. And then we're going to run our convenience sample. So you're going to have a data frame with 8 rows of data by 3. So you've got your row number being 8, 1 to 8, and then you've got your ID, which is an integer, being 1 to 8. You've got your group, which is a character, being all A's, and then you've got your value, which is a value that you've selected. So the problem that you have with convenient sampling is that you're sampling the values that are most convenient to you. So whenever you carry out convenient sampling, you're probably not carrying out the best type of sampling because you're not getting a proportional representation of the sample because you're just sampling elements that are close to you. So that's a problem that you're going to have with convenient sampling, but it is a type of sampling, and that's why it's included in sampling types, even though it's not the best way to sample, and it certainly is probably not going to give you a very accurate reading. So that concludes this video. The next video is going to be another topic on inferential statistics, and so I hope that you decide to watch it.